So now we are recording. Let us look at this central limit theorem one more time. Yesterday, whatever we have started, maybe 5 minutes. In the meantime, other people will join. Central limit theorem gives us actually three things. I actually kept it in two things only. One is mean of all the sample means is going to be equal to population's mean. Second thing is sampling distribution of means is always normally distributed, and the sampling distribution's mean is going to be population's mean mu, and the sampling distribution's variance can be calculated using sigma square by n. Our sampling distribution of means are different samples. All the samples means variance can be calculated using sigma square by n or sigma by square root of n. The standard deviation is sigma by square root of n. So these are the given things. And yesterday we actually tried to look at, is that really true or not by taking some examples. We actually looked into some video and then, we looked into the examples also. Right. So here we have taken the, first whatever first point we are trying to explain here. Right? We have 2 lakh apples with a mean of mu and variance of sigma square. Suppose that you have taken many samples of 36 apples, and each sample you took mean. And when you take mean of all these means, that is going to be equal to the population's mean mu. Okay. So the population's mean mu. Okay, that is the first statement. The second statement is, when you take many samples from the data and take means of them, those means are going to be normally distributed. Those means, x-axis are all mean weights, y-axis are number of samples. Okay, number of samples. Each sample mean is on the x-axis. So, number of samples means this mean only 2 samples. This mean 4 samples have got the same mean. Around 6 samples have got the same mean. 8 samples have got the same mean. Again, 6 samples, like that it is. Okay. So, and the mean of these means is going to be population's mean mu, and variance of these means is going to be sigma square by n. Let me check whether the recording is happening. Oh, is there a background noise for you all guys?
Yes, Rama, someone has not muted, it seems.
Okay. Should I have how to look at all the participants here? Let me mute and check, whether it is from my side or not. Okay. Yeah, I'll mute it.
Yeah, it looks like from your side only.
Okay. So let me, log in, I'll leave the meeting and log in again. Okay. Give me 1 second. Okay? So I have taken out the video and now logged in back, log back in. How is that? How is the noise thing now?
It's the same.
Is it too annoying?
Not that much, but it will be a little bit disturbing when people hear the recording.
Okay. Maybe because of the Unix machine, right? I logged in from Unix machine, right? Maybe because of that.
Yeah, maybe.
Yeah. So Shall we continue or should I come back in the Windows machine? Leave and come back in the Windows machine.
I think we can continue.
Yeah, we can continue, Rama. It's not that much noise. We can continue.
Okay. Tomorrow I'll log in from the Windows machine. We'll check which one is. But anyway, when we start deep learning classes, right? I'll be joining from Unix machine only. So we'll see.
Okay.
Maybe internet is also an issue. My router got got corrupted. It is actually dropping some packets there. I bought a new one. I'll receive it this weekend. So from Monday we'll not have these problems. Okay. So that may be because of the router also. Router got corrupted. It is actually dropping the packets, and on mobile I am not getting good speed. On Windows, sorry, on computer I am getting good speed. So maybe because of that also. From Monday, right, we'll not have that problem. Tomorrow we'll anyway log in from Windows machine. Okay. So this is central limit theorem. Okay. Using central limit theorem, we actually did something. But before that, right, I took a normally distributed data and then tried to do sampling distribution of, I have taken 10,000 samples of size 5 and 10,000 samples of size 20. And when I took the sample size, bigger size, right, the what you call it as the normal distribution is steeper. The sampling distribution of means normal distribution is steeper.
The participant list actually.
Sorry?
I'm seeing the list of participants, not seeing the screen.
Oh, really? Maybe I didn't share my screen. Sorry. I logged in back, right? I forgot to share my screen. Sorry. You can see now, right?
Yeah.
Yeah. So, when you take sample size is small, the spread is going to be more. What is the problem with spread? When you have more spread or more variance, what is the problem? Is there any problem in making predictions if the spread is more or making a decision? Is there a problem when variance is more? If the data is like this and like this, what is the advantage of having data like this?
Prediction will not be accurate.
In this, right?
Yeah.
In the second one, prediction will be accurate.
Yeah, if you take mean as the prediction, right? If you take mean as the prediction in both the cases, here the prediction is not going to be that accurate. Here the prediction is going to be more accurate because all the data is close to mean, right? All the data is close to mean. That point you need to remember. We can calculate standard deviation by using the individual means and taking mean by putting into the formula, standard deviation formula, or you can use standard error formula. What is standard error? Sigma by square root of n. This number and this number are going to be close. So both ways are valid, but this way is like useful when you are actually trying to infer from the samples. We'll see that example. I've shown you an example yesterday. We're going to see the same example today also. And when the sample size is big, 20 samples, the standard error and the standard deviation calculated of the means is equal. No need to do all this math. We just need to imbibe the concept. So I'm actually explaining this many times. This is very important. This is very, very, very important. If you don't understand normal distribution, stop and ask me. Even if it is needed weekend, I'll take a class. But definitely you should understand. Okay. So on a non-normal distribution also, when I took many samples, the samples means are always going to be normally distributed. This is very important. In real-time scenarios, we don't know how the population is. But when you take many samples of the same data, many samples of the data, samples from the population, you will get normally. When your data is normally distributed, you have 3 sigma rule where you can calculate probabilities and all that. So that is this example, right? We have 36 apple sample from 2 lakh apples, and the mean of the sample is 112 grams and standard deviation is 40 grams. We don't know whether mean is normally distributed or population is normally distributed. But we know from center limit theorem that when we take many samples of 36 apples like this, right, the means are going to be normally distributed. What we need to find here, we need to find the mean of the population, right? Mean of these 2 lakh apples is going to be within this range. What is the probability we need to find? What is the probability means? At what range it is going to fall, right? So when you take many means, right? Sir, could you please mute? Somebody is not muted. So when you have question, you can unmute. So when you have now, when you take many means, like many samples and means of them, that those means are going to be definitely normally distributed. And what we need to find here, fortunately, we need to find the mean of the population. Is falling within this range or not? What is the probability? So when you take n number of samples, if most of them falling in a range, right, in this range, right, 95% of them, 95% of the samples, 36 apple samples are falling within this range, we can say we are 95% confident that the population's 2 lakh apples mean weight is going to fall between this range. Did you get my statement? The last statement. We have to find the probability of mean weight of the apples. Mean weight of the apples means you take 2 lakh apples and calculate the mean weight. Each apple you take and calculate the weight and then take the mean of it, and that mean is going to fall between 100 and 124 grams. What is the probability? That's the question. Okay, you got the question clearly? Yesterday itself you got it, or today?
Yes.
You got the question clearly, right? So
Yeah.
mean weight of 2 lakh apples is going to fall between this range. And what is the probability? Because you cannot exactly say that the mean weight is this, because you cannot calculate weight of each apple and calculate mean, right? That's the problem. So we need to estimate. We need to estimate the mean weight of the 2 lakh apples, and then when you are estimating, right, there will be a range. You cannot exactly say. There will be a range, 100 to 124. What is the probability? If most of the samples, right, I took 36, 36, 36, 36 like this. If most of the samples means 95% of the samples, mean weight is between 100 and 124, what we can say? You took 100 samples, out of them 95 samples, mean weights are between 100 and 124. Then what you can say? 95% I am confident that these 2 lakh apples mean weight is going to be between 100 and 124. Can I say that? That statement you understood, right?
Yes, Rama.
Okay, so that's what we are trying to do. So here what we have is 36 apples, mean weight is 112, standard deviation is 40. What to do, we already know. So what I did, I actually assumed that I have taken many samples of 36, and those samples mean is also 112, because I have only one sample, and that's what I have. So I have to use that and use it. You do something, right? This is like a population's mean is 112 and population standard deviation is 40. That's what I thought, right? And then when you take many samples, the mean here is going to be 112. Okay, the mean is going to be 112. I can calculate the standard deviation of the sampling distribution of mean. I can calculate even though I don't have many samples chosen, right? I assumed it here, right? When I assumed it, I will not have mean weights of many things, right? If I have mu1, mu2, mu3, mu4, and so on, mu100, I'll be able to calculate the mean of all those means, and then I would have calculated standard deviation of this. But I don't have that possibility here because I don't have 100 samples chosen. I am assuming that many samples were chosen. So when I assume, I know that the sampling distribution of means is going to be normally distributed. I have one formula, right? The standard error formula, which will give me access to calculating the standard deviation of the sampling distribution of means, right? So using that formula, right? Here I said that we can calculate the standard deviation of the sampling distribution of means. When samples are available, Anyway, you'll use the formula and calculate it. Use the actual standard deviation formula and calculate. When samples are not available, you need to assume some things and then calculate the standard error. Did you get this point, Ganga Devi? I think yesterday you asked this question, right? I don't know whether you are there or not. I cannot see all the participants. So, yeah.
Yes.
Now you got the clarity, right? Here.
Yes,
Why
sir.
this formula? Why this formula? Because when you are actually trying to infer something about less number of samples, right? When you have only less number of samples, here is the situation. Only one sample we have, and one sample's data we have, and you cannot calculate means of all those samples, and you cannot use that original formula of variance and standard deviation. Now we are using, the formula for this standard error. What is standard error? Sigma by square root of n. Population standard deviation by sample size. Here I am saying 36 samples, 36 apples in each sample. So n is going to be 36, and I assumed that 40 is the standard deviation. When I took one sample, the standard deviation was 40. If all apples are of equal size, right? What would have happened? Whenever you take a sample, the mean would have been close to 112 and the standard deviation would have been close to 40 if all the apples are of same size. We are assuming, right, similar samples will be taken. If your sample taken first time taken sample is wrong, then your whole calculation will go wrong. That's where when the exit polls were done, right, Bihar case, right, exit polls were done, total thing will flip, right? You got it. You are getting it, right? Real time examples and central limit theorem. This is how they actually do the exit polls analysis. Okay, I calculated standard deviation, which is nothing but standard error. This is not exactly the original standard deviation of this sampling distribution of means. It is an estimate. Okay. In this estimate also we assumed something. 40 is the population standard deviation. We assumed, right? So this is all assumption. Whatever you have, you will take that and try to infer something. Now you know the standard deviation, you know the mean, right? You can calculate one standard deviation away and two standard deviations away, right? 98.66 is the mean of some sample. 125.34 is mean of some apples, right? Some sample, and between these two, 95% of the data is falling, or 95% of the samples are falling. That means what? 95% confident that mean of the top population is going to be between 98.66 grams and 125.34 grams. Is this clear? Many times I took samples. If I take many times samples, all the samples means are actually falling in this range. That means total 2 lakh apples mean weight also may fall in this range. We are 95% confident, 95% confident that the range, right? It can be, if you take the 2 lakh apples, the 2 lakh apples mean can be 98.66 or 100 or maybe 112 or maybe 125.34, right? Any number between this range. We are 95%. 95%. We are very confident that we can say the mean of apples is going to fall between this range. No, rough estimate it is, right? 95% confident. We cannot give 100%. That's where 99.7% is the 3 standard deviations. Like most of the data is going to fall between 3 standard. Now, if your apples are of small size or big size, if they are big size, right, it's going to be the mean is going to fall at this end. If all the apples are small size, it's going to fall at this end, right? The mean is going to fall at this end, right? So we calculated that confidence interval and the percentage, right? The confidence score, we call it as 95% is the confidence score, and this is the interval. Okay, so we did not calculate exactly, right, 100 and 124. The question was that the mean weight is going to be between 100 and 124 grams, but here we just said that approximate, right, and it is a little less than 100 and a little more than 124. we can calculate exact also. This point till here you are clear, right? No questions? I think you are good, right?
Yes, Rama.
Good. So now, right, we can calculate exact also, right? I think in, when I studied MCA, right, my statistics lecturer used to ask me to bring the tables. Right? There is a book with all these statistical tables. I don't know why I'm using that, and even the professor doesn't know why he is explaining also. Now I understand after 20 years of industry experience, and now after getting into AI, I got to know why these tables. Okay, so this is the table. If you look at this, I don't know whether you can see it clearly or not. Let me try to magnify this. Can't I drag it this time? That's right. Yeah. See, if you look at this table, right? If you look at that graph, right, this table is actually showing you the area under the curve from this place to this place. What does that mean? Is if you take if your Z score, right, Z score. This is all Z score. What is Z score? We can calculate Z score of any mean, any apple mean, right? Any apple mean, we can calculate Z score. Suppose that the samples mean is 100, right? If you want to calculate the Z score, what is the mean of all these means? 112, right? Do you agree? What is the mean of all these means? 112, right? And I am calculating Z score. What is Z score? X minus mu divided by sigma, right? X is 100. What is X here? One of the mean, right? I am trying to see here, right? What is the Z score? What is the Z score of 98.66? What is the Z score of 98.66?
98.66 minus 1112.
By standard deviation.
By standard deviation, right? What is it? It is -2 actually, right? I said 95% confidence interval, right? The Z score of 98.22 is -2. Let's calculate that. I think you got formula, but when you look at a normal distribution and 95% confidence interval, right? It's -2 and +2. Let us see that. That point you need to understand. Right? What is that? You said 98.66 minus 112, right? Divided by 6 point. What is that? Standard deviation is how much?
6.66.
6.67. Yeah, 6.67. 6.67. See that it is -2, right? And what is the standard deviation of 125? 125.34. What is the Z score? Sorry, what is the Z score of 125.34?
+2.
I think +2.
+2. Yes, sir. +2. What is the Z score of 118.67?
+1.
+1. This is -1, right? So the Z scores, standard Z scores like -1, -2, +1, +2, -3, -2. We know the probability, right? We know the 95% confidence and 68% confidence. But the other areas, right? Other places, if I calculate Z score of 100, right? It is -1.799. It is -1.8. I can say, right? If I round it off, I can say -1.8. What is the probability? -1.8, or +1.8. What is -1.8? Like this here. On a normal distribution, this is -1.8. Okay. If you want to know what is the probability here, you need to know the area under this curve. The area under that curve will give you the probability, because the total area under the curve is 1, right? The area under this piece is going to give you the probability of that area, right? From 0 to, right, from beginning to that particular -1.8, it will give. Right? To find out that value, you use this table, and this table will have positive ones only. From here it will have the values. Okay, so from here it will have the values. If I say minus 1.8 and 0.00, right? Minus 1.800 minus 1.81 minus 1.89 is also there, but I am taking minus 1.88 is 0.9641. What is this 0.9641? From here till here, the area under the curve or the probability. Got it? Got it? In 3 sigma rule, right, what are we getting? The area under the curve from here, minus 2 to minus 2 plus 2, minus 1 to plus 1, minus 3 to plus 3. But the table gives you from beginning till the positive probability, positive z-score. Got it? Got this? What is this? 0.9641. Did you get what this number is? Any questions? If nobody asks question, right, I think you got it.
No, no. How do you get that 1.8 standard deviation here? 100 is 1.8.
1.8 is the z-score. Z-score of 100.
G-score of 100 is 1.79. Okay, okay. We consider it as a 1.8.
1.79. I round it up. Or rounded it up. Just for
Okay.
explanation purposes. Right?
Okay.
So 124 is point plus 1.8 and 100 is minus 1.8. See this 124 minus 12 divided by
Yeah.
6.61.
But in the G-score, we always consider the positive one only, plus one, right?
In this table, right, it considers only plus positive one, right?
Okay.
And then it gives the probability area under the curve till that point, from here till that point, all this filled area. Okay. What we need to
So
find?
this G-score table is the standard one.
Yeah, this is a standard one. This is a standard one.
Got it.
In statistics classes, right, we'll use it. Actually, in BTech and MCA, there will be statistics concepts.
Okay.
And the courses were designed very well, but the professors who explain are not so well. That's where we will not get that quality. Right? Maybe after you strive a lot and you get it, like these kinds of real time problems you get into and then solve, then you get it. Right? So what we need to find is from minus 1.8 to plus 1.8, what is the area under the curve? Because the confidence interval is 100 to 124 and we need to find out the confidence score, right? So from here till here we need to find that is the question we are trying to answer. To calculate this, right, we got from here till here, right? From here till 1.8 we got. We know that half of it is 0.5. Do you know that? The total area under the curve is 1. If you split it into half, the first half, the green dots area is going to be 0.5. You agree with this statement, right? Right? Do you agree?
Yes, yes.
Yeah.
So if you subtract this total area, this green area, from this blue area, if you subtract this green area, you get this area, right? What is this? From mean to 1.8, from 0 z-score, from 0 z-score to 1.8 z-score, it is 4.441. If you double that, right, it is just that, one side you found it, you double it, you got the total thing, right? 2 into 0.4641 is going to the area under this total thing, minus 1.8 to plus 1.8. That's how I found that 92.82% confident that the population mean weight is going to be between 100 and 124. Got it? Got it? Any questions?
Yeah. So this 9641, you got it from the table.
Here. This positive, if you z-score, right? What you should do is you should take the positive z-score value and then apply this kind of a technique. Subtract the negative and whatever. Right? Got it? Or if you get only negative z-score, right, minus 1.8, right, you calculate till here, right, this area and this area are going to be equal, right? Whatever the area under the curve you calculate, the total 0.96 whatever, 1 minus that is going to be this. Whatever, that don't get confused. If you get this right, that's enough. Okay. So you got this right? No questions, right? So that is one example of statistics and how the central limit theorem is useful. Especially the standard error is useful. We will actually connect machine learning with these all terminology, right? By Friday, by tomorrow, or not tomorrow, by Monday, right? We'll actually connect all these dots. We are learning statistics, right? We'll actually connect the statistics to machine learning. There are places where you use the all these concepts, the standard error, standard deviation, and all these concepts in machine learning. Okay, so I am actually jumping into the next topic. If you are all clear on the central limit theorem and the application I showed, this is just to understand or imbibe.
Sir, one more thing. So this table and all is already built in some libraries.
Yeah, it is all there. No need to worry. You know, if you take SciPy, there will be everything there. You can just call the method and it will actually do it for you. And we will not solve this kind of problems in our real time. This is just to show you the importance of central limit theorem and the standard error. I've taken this example. And how statisticians were actually calculating confidence interval and how this exit polls is happening. That's a interesting question I had. So I tried to solve that here.
Okay.
So the
How did you
SciPy will have all the methods. Yeah, go ahead.
how did you pick that value, sir? 0.9641 from that table. I didn't get exactly.
Okay. So the question is, what is the question here? We need to find out total population's mean weight is going to be between 100 and 124, right?
Yes.
So 100 is some samples mean, right? Do you agree?
Mm.
124 is also some samples mean. Okay. If you take your data, right? If you look at this diagram, 98.6 is some samples mean, right? 125.34 is some samples mean. But when we look at that, it is 95% confidence interval, right? But there is 100 here, right? There is 124 here. Do you agree?
Yeah.
Right? For those, right, if you know the z-score, right, you can actually look at the area under the curve. What is the thing we need to get? We know area under the curve between this 98.66 and 125.34, which is 95. Okay.
Yes.
Right? So we are able to say we are 95% confidence that the mean weight is going to be between 98 grams and 125 grams. Okay. So we have to find out the percentage for 100 and 124. Okay. So to find out the percentage for 100 and 124, we have a statistical table which gives you area under the curve by taking the z-score, z-score. Okay. So this is Z score. I think you can see this with a very small number. Right? First, what we need to do is for 100 and 124, we need to calculate the Z score. Okay. To look at the area under the curve from here till here. Okay. When we know the area under the curve from here till here, we can calculate the area under the curve from 100 to 124. For 100, the Z score is minus 1.8. For 124, the z-score is plus 1.8. When you look at plus 1.8 and the value there, it is 0.9641, right? This total thing is 0.9641. I actually calculated some, I subtracted this 0.5. I got this area. I doubled it. I got minus 1.8 to 1.8, which is nothing but 100 to 124. Z-score I mentioned here. 100 is the actual mean. 124 is the actual mean. Z-score of 100 is minus 1.4. Z-score of 100 is 1.4. 124 is 1.8. So this area under the curve is this much. 0.9282.
Oh, okay. Yeah.
Got it, right?
Thank you. Yeah.
Yeah. So you should always be connected with the business. When you are looking at numbers, right, we'll get lost in the numbers. So that's what, when I was studying statistics in 20 years ago, I always got lost in numbers, not connected with the business. That's where I couldn't get it. Now I am getting it because I'm always be connected with numbers, the business. Right? The 100, the mean weight. The 124 is mean weight of sample. Yeah, go ahead.
So we are actually checking on the 0.00, right?
0.00.
In the row.
No,
So 1.8.
1.8.
Yeah, 1.8 in the top.
1.8.0. 1.80 it is, right? 1.89 is going to be this value. 1.88 is going to be this value. 1.87 is going. Actually, we should have taken 1.799, right? Only 9 is there. We'll round it off, and maybe we would have taken 7.99, right? So it's going to be 0.99633. Either 0.9633 or now 0.9641 is like not a big deal, right? So I took this one.
Okay, understood.
It's an approximation, right? It's an estimation. In that estimation, no perfection is needed. Here and there, a little bit is.
Yeah, understood.
But this, whatever the point you are trying to take is, when you are launching a rocket, right? The decimals at the 10th digit is also very important, because you are going to project the rocket like this. It is going to go like a parabola, right? When you shoot it, it's going to go like a parabola. Even if there is a minute difference in the angle, right? This angle will become big when it goes to the moon, right? Moon or Mars, right? It should be so perfect. The software, the language we use, Fortran is actually scientific language, they say, because it actually can calculate more decimals very accurately. C language is like scientific language. But if you take basic kind of a language, right, it cannot calculate the decimals very big decimals. It after 10 zeros and 1, right, it will consider it as 0, but it is not, right? That angle is not, that 10th digit angle is also difference, right? The difference will go very big when you launch it. So that is where we used to say Fortran is a scientific language, C is very good language, because of these things. When we do small, we will not understand. When we do these kinds of big things, right, we'll understand. Here it is statistics, so that's okay. It's anyway estimation, right? If you look at this, right, these are all blunders. If you look at it carefully, right, or in a sensible manner, I am taking a samples mean standard deviation as population standard deviation. One samples mean as population's mean, or mean of means, 1/4. These are all blunders. After that, right, if you take care of that 0.33 or 0.41, that doesn't matter.
Rama, like here we actually got the standard score as -1.8 and +1.8 for values 100 and 124. So let's say if we take some other number and these scores are not exactly the same, positive and negative. So how can we calculate?
We can. Then also we can actually. If it is not positive and negative, right, what we should be doing is, suppose that, let me take an example. Anyway, we are not going to do this in real time, right? But let me take a screenshot of this, and then let me open that. Anyway, we are not going to do this, but I'm just trying to explain as you asked. May not be waste of time, because this is useful only. So if you, I think I should magnify this out. But what you are saying is, if I took some other number here, right? Maybe 121, right? Here I took 80, right? For 80, I would have got maybe some z-score of -1.3, right? So I need to calculate, -1.3, and for 124, it may be 1.5. Okay, suppose that, right? Now, For 1.5, what is the area under the curve? This is the area under the curve. For 1.3, this is the area under the curve. Okay, so let us take it. Give me 1 second. So this curve, right? And then for 1.3, we need to find out this area minus 1.3 and 1.5. Okay, so first what we need to find is, let me take another color. First we need to find (0 to 1.5). Okay, this area we need to find. Then we need to find (0 to 1.3). Okay, either this side or that side is same, right? You need to find, actually we need to find this area, right? So that is going to be sum of this area plus this area, right? You can find this area and that area, because for 1.3, from beginning till 1.3 is how much? 0.9032, right? This whole area. If you half it, right, this is going to be 0.5. If you subtract 0.9032 minus 0.5, how much is that? 0.4032. So this area, right, this area is going to be 0.4032. Got it? 0.4032. Got it? How did I calculate this area? I took the area from here till here total, and I subtracted this part, right? I got this area. What is that area? 0.4032. Got this point?
Yes, yes.
Right? How will you calculate this 0.15 thing? Again, you take the total thing, right? 0.9332, right? This is total area. Again, you subtract a half, right? It is going to be 0.4332. Right? When you sum up these two, 0.4332, and give me 1 second. Hello? Yeah. Good morning, Andy. ఎవరు సాహు సార్ అండి? సాహు సార్ చెప్పారా మీకు? నేను క్లాస్లో ఉన్నానండి, మళ్ళీ కాల్ చేస్తాను. నేను ఒక 1 అవర్లో కాల్. So that's how we calculate. We sum up these two and you get the total area under the curve. You get total area under the curve, right? Got it?
Yes.
Anyway, we'll not do that, but when you do this kind of an understanding, you understand that the area under the curve is 1, and you can do that manipulation. This is useful. This is useful. The conceptual thing is very useful. We may not do, we will not do this any place in our course or real time. We will not do this, but conceptually you should get complete grip on it. Any other questions?
No, I'm good.
Okay, so if we are all good, right, I'm moving on to a concept called as p-value, statistical significance and p-value. Give me 1 second. So statistical significance and p-value, right? So if you look at the statistical significance, right, in a layman's terminology, okay, uncommon things are significant, right? Human beings generally think like that. If a person is flying, right, it is very significant. We can walk, we can run, we can do many things, but these are all not significant. If somebody is flying, right, it is very significant. Uncommon things are very significant. That is the statistical significance test. Okay, so we test whether or not. Test. Now there is a drug already working. Right? Somebody else found another advancement to the drug. We need to prove that the new drug is more advanced or more significant than the current existing drug. Okay. In some cases, what happens is the difference between the current drug and the new drug is minute. Right. The current drug may be working with 99.9% accuracy. Right. 99% of the times it is working. COVID vaccine. Right. The Pfizer guys are actually saying 95% it is working. The 0.5% is kind of a lucky dip, it seems. Right? After taking the vaccine also, if it did not work, they'll say like you fell under that 5%. It is like that, right? So what is the use of taking that vaccine? I'm not trying to belittle the research they did for one year, and they're trying to help people, but conceptually, if you try to look at it, right, it is like they found a vaccine and they are going to give it. We have to pay for it, and by chance, if you get it right, if somebody gets it, they'll say that guy fall under that 5%. That's like that, right? So a drug is there already, which is working 99% of the times, and new drug is working with 99.5%. Right? It is just that 0.5% difference. So you may not be able to see that significance clearly when you look at the experimental results. At that point in time, you need to do statistical test to identify the clear difference. Okay, when the difference is very minute, statistical significance tests will let you know whether it is really significant or not. Okay, to do the test right, to make it to actually prove that it is significant, initially we'll take that it is not significant. That is called as null hypothesis. Generally, whatever experiments outcome, we say not significant, or whatever generally accepted fact, we say null hypothesis. What is generally accepted fact? Drug is working 99% of the times, and new drug is working 99.5% of the times now, right? So we'll say no, there is no effect of your drug. 99.5%, no, there is no effect. We'll say that is the null hypothesis, right? It is like, I don't know whether you remember it or not. In mathematics, there were theorems, right? We start with negation, and we say, right, the negation is false, and then say we accept it, right? Like that. Negation is false means something else may also be possible. It is not that A is not, there is no yes and no only in the world. There is no yes and no, and others also there are in the world, right? In real time, and people, especially human beings' behavior, there is not just yes and no. There are many things, but mathematics, it is only yes and no. That's the flaw in mathematics. That's where computers are not being able to do all the things human beings are able to do, because we always take 0 or 1. Quantum computing is all about that. It will be between 0 and 1 also. It's like, I'm not going to go into those details, but here we are trying to understand what is null hypothesis, what is alternate hypothesis, what is statistical significance. Okay. So when some experiment is done, every time new experiments will be done, right? There will be some research, some finding, we'll be using it, but the researchers are striving to find new things which are better than whatever we have right now. That betterment may not be that significant, but the significance should be tested and found out. The statistics is useful in doing that. So in layman's terminology, uncommon things are significant. Uncommon things are significant. If a person can fly, it is significant. If a person can lift 1,000 kilos of weight, it is significant, because most of the people cannot do, right? So if a task can be performed by very less people, the task is significant. In layman's terminology, I'm talking. If you look into statistics definition, right, you lose your mind. Okay, I actually lost my mind and I actually tried to settle it with these layman's terminology. If a task can be performed by very less number of people, the task is significant. If a certain outcome of an experiment can be achieved by having certain environment, the experiment is significant, right? Drug, device, or condition. In some conducive environment, if you are able to produce something, right, the experiment we say that is significant. The conducive environment is also needed to get that result. Okay. So let us look at a little more and then I'll stop for questions. Okay. So this is a bit bit here and there thing, right? Even if you don't understand, right, don't worry, because I'll explain this again and again. If you have questions, we'll discuss. Even today we'll discuss. A weekend also you can discuss. But when Bala and Keshwa are explaining, right, they may explain a different way and you may get confused, right? Don't get confused. If you have confusion, right, Monday we'll discuss again. Okay. I am trying to explain concepts very patiently because these are all very important. And for 1.5 months, right, we'll go like this only. From that point onwards, it's going to be bombarding. Okay. So you don't think that I'm going slow. You need to get these concepts. Once you get these concepts, rest is all piece of cake. Okay. So let us try to understand what is null hypothesis. Is a commonly accepted fact, right? Suppose that Newton found out that the gravity is 9.8 meters per second. I don't know whether it is correct or not. Right? I came in and said, no, it is not 9.8, it is 10. Right? Null hypothesis is going to be gravity is not 10 or gravity is 9.8 only. Right? Generally accepted fact is whatever Newton said, right? Whatever I said is not generally accepted fact. So null hypothesis we will take as that, right? The null hypothesis we call it as null because the researchers want to nullify nullify this. Whatever generally accepted fact they wanted to nullify it and find out a new thing. Okay, that's where we call it as null hypothesis. Generally accepted fact is null hypothesis. Alternate hypothesis is opposite to null hypothesis. This is not true, we say. It is not 9.8. It can be greater, it can be less. That is alternate hypothesis. Right? There is a concept called as p-value. The probability, the p-value is the probability of getting the observed result of the test if null hypothesis is correct. Okay, this statement is what we need to understand. The p-value will actually do something and find out p-value. How to find out, I'll explain. The p-value is the probability of getting the observed result of a test if the null hypothesis is correct. Right? What we are going to do is, if you look at this, right, if a certain experiment outcome is, if a certain outcome of an experiment can be achieved by having certain environment, I said, right here. Certain environment means I found a drug, and the drug to work, the temperature in the room should be around 30 degrees. Okay. So to find out p-value, what we will do is we will not put 30 degrees temperature and try to give the drug and see how it's working. Right. So at that not 30 degrees, at that kind of particular, wherever that new experiment is conducted, those environment conditions are not there. That means null hypothesis situation we have seen, right? What is null hypothesis situation? A drug was there, which was given, right? Oh, sorry, I kind of said something now. A drug was there, which was given in normal temperature. They never controlled the temperature and gave the drug. It was working 95%. 95% of the times it is working. Okay. Now the new drug came in. Right? Now the new drug came in, and this new drug, I am saying your room temperature is 30 degrees and you inject the drug, it is going to work 99% of the times, I said. Right? And you said, right, when I said at 30 degrees of temperature, my drug will work better than your drug. You said your drug is not working, right? That is null hypothesis. your drug is not significant. 30 degrees temperature is not significant, you said, right? Or your drug is not significant. Okay, so let us try, when you say it is not significant, right? What you are saying is my drug will also work in normal room temperatures and it will give 99% accuracy. Okay, so you said that when you said null hypothesis, what is null hypothesis? Your drug is not significant, you said. That means what? Your drug is also working. My drug is not significant, you said. So that means your drug is also giving 99%. Let us check it. How do you check it? In a null hypothesis situation, we will try to give the drug and see how it's working. Okay. If it is working 99%, right? Then whatever my thing is not good, whatever my thing is, it is not significant because old drug is already working in normal temperature, right? No need to put 30 degrees temperature and do whatever I wanted to do, right? Getting it? Getting it? So we are going to do the experiment in the null hypothesis situation, not putting all those new conditions, and do the experiment and find out the value, find out, out of 100 times, how many times it is working. Okay. If the p-value, right, if the p-value is greater than 5%, right, greater than or equal to alpha, we say this is actually a thumb rule. No, we'll accept the null hypothesis. If it is less than 5%, right, we reject the null hypothesis, right? So here in this situation, right, when the new condition was not set and still the drug is working, that means new drug is not significant. You can actually accept the null hypothesis. That is, even when the temperature was not changed, the drug is working, right? The drug is working. So your drug is not significant. I'll accept null hypothesis and my drug is going to go into trash. Okay. If it is not, right, if it is not working, then I say your drug is somewhat significant. Right, we reject null hypothesis. Okay, so there is some probability value we need to calculate, and if the probability value is greater than 0.5, we accept the null hypothesis. If it is less than 0.5, we reject the null hypothesis. Let me take a simple example, not the drug one. I said human being can fly. Okay. And generally we know that human beings cannot fly, right? So if more than 5 people can fly, right, I'll accept null hypothesis. Okay, I'll accept null hypothesis. That means what is null hypothesis? Okay, sorry. Right. The null hypothesis is going to be what? Human beings cannot fly. Okay. I said human beings can fly. That is the new thing I found. Okay. The null hypothesis is going to be human beings cannot fly. Okay. If you take 100 people, out of those 100 people, less than 5 people are flying, are unable to fly, right? Then we say we accept null hypothesis. Right? What is null hypothesis? Cannot fly, right? Cannot fly. Yeah, right. More than 5 people. Sorry, more than 5 people. Right? Maybe out of, I have seen one person who is actually flying, and I took 100 people. I challenged you, saying that human beings can fly, and you said no, human beings cannot fly. You took 100 people, right? Out of them, the person I have seen also is there, right? That person is flying, and the rest all are not flying, right? Out of 100, only one person one person flew, rest not flew, right? 99 people did not flew. That is greater than 5%, right? 0.05 means 5%, right? Greater than 5% of the times, whatever the statement you made is true, so we have to accept it. When you are doing the hypothesis testing, even if it is only 5 people cannot fly, right? More than 5, right? 6 people cannot fly, I'll accept the null hypothesis. Did you get it? Did I confuse you? Did you get it? Get anything at all? A little bit also?
Confusing, sir.
Confusing? Okay. Let me take another example. So we'll not take this example. This was a bit more confusing. I tried this in the last batch. So let me take another example. Give me 1 second. Yeah, 100 kilos of weight, right? So yeah, I made a statement saying that anybody can lift 100 kilograms of weight. Okay, that's a new finding I did, right? The null hypothesis is going to be opposite to it, right? Opposite to it are generally accepted fact. What is generally accepted fact? Can everybody lift 100 kilos of weight? Can everybody lift 100 kilos of weight?
No, sir.
No, right? So that is null hypothesis. Okay. Now we are trying to find out p-value. Based on the p-value, we are going to accept or reject null hypothesis. Okay. What is p-value? You take 100 people and give them the 100 kilos weight. Ask each one to lift it. Okay. Now, first one couldn't lift it. Second one couldn't lift it. Third one, fourth one, like that. 6 people lifted it. Okay. 6 people lifted it. P-value is going to be probability of getting observed results on the null hypothesis when null hypothesis is correct. So I think I have to take another parameter there, right? Steroid, maybe we injected steroid and then asked people to take it. When steroid is there, people can lift 100 kilos. When steroid is not there, people cannot lift. So you said the statement is like this. Let me write it down. Sorry. Let me write it down. This is a bit confusing concept, okay? So, but we need to understand this because now we'll see the p-values in linear regression algorithm. Right? So the statement is like this. My experiment, right? My experiment. I have a steroid. Okay. And when I inject it, people can lift 100 kilos, 100 kg. Okay. So this is my statement. This is my statement. Now, null hypothesis. What is null hypothesis? Null hypothesis is, right? People can lift 100 kilos even when the steroid was not injected. Even when, in general, I will say in general, right? 100 kg in general. Right? What I said, your steroid is not significant. That's what I said. Right? The test is about the steroid, whether steroid is significant or not in making people lift 100 kilos. Till this part, you're clear, right? Till this part clear, right?
Yes.
Right? Null hypothesis should be taken like this. Okay. In general, when the steroid was not there, also you can lift. I said. Now I took 100 people. Maybe I'll take this as 900 kilos. No, this is confusing. 900 kilos. I have taken 100 people. Okay. I asked, I did not give the steroid and asked people to lift it. Right? First one came on, P1 came, did not lift it. P2 did not lift it. P3. These people are not injected with the steroid. Okay, no. P4 lifted. P5 no. Right? Like that, P100. I actually looked P100 people I looked into. Now, wherever we get yes, right, we'll count. If the count is 3, right, the P value is 3, right, or 3 by 100. P value is going to be 0.00003, right? Right? 003 or 03?
No, 0.3.
0.03.
0.03. 0.03, right? 0.03, right? Now P value is 0.3. What is it saying is if P value is less than 0.05, 0.05, we reject the null hypothesis. Okay, we reject the null hypothesis. In general, people can lift 900 kilos. We reject it. That means the steroid is significant. Okay, suppose that, right? Suppose that out of this experiment, right? First one lifted, second one lifted, third one lifted, fourth one, fifth one also lifted. Like around 10 people lifted. Then P value is going to be 10 by 100. It is going to be 0.1, right? 0.1. That means what? This is actually greater than 0.1 is greater than 0.05. So we accept null hypothesis. In general, the people can lift 900 kilos. Got it? To make your new outcome significant, in general, less than 5% of the times it should happen. Okay, this is called as alpha, the significance level. This is called as P value. When null hypothesis is true, in the situation where null hypothesis is true, that means no steroid injected. I took 100 people, right, and asked them to lift 900 kilos, right? 10 people lifted it. The P value of this experiment is 0.1. The significance level is 0.05. Okay, the significance level is 0.05. The P value of this experiment in null hypothesis situation is greater than 0.05. So, right, I reject null hypothesis. When P value is greater than the significance level, I reject null hypothesis. In general also, even when your steroid was not injected, 10 people are lifting out of 100. No significant. Okay. In general, if people are unable to do it, it is significant. When you actually injected it, in general, people are unable to do it. When you injected it, people are able to do it. That is significant, right? The uncommon things are significant. That's the point. Okay. 5%. Less than 5%, uncommon. More than 5%, common. Got it? More than 5% common. More than 5% common. So you rejected. So you accepted null hypothesis. I think I'm confused. Right? Accepted null hypothesis. You must accept null hypothesis. When it is less than 0.05, right? You reject null hypothesis. Right? Uncommon. 5% is the uncommon thing. Less than 5%, uncommon. More than 5%, common. Got it? Is it clear now?
Yeah, probably instead of saying common, we better say significant. Maybe that gives probably effectiveness around that, right?
Yeah, significant.
Yeah.
Whichever the way I take it, significant.
Yeah, sure.
Some people take it this way, some people will take it that way. Right, so. Got it? Any questions here? Still not getting it? This is very, this is very confusing concept, but if you understand it once, right, you will remember it. Even now I get confused sometimes. Previously I was explaining, right? And I was actually explaining this for last 3 years and using it for last 5 years. Still I am confused. So don't be worried. See, the experiment, the statistical significance test is for the steroid. When steroid is injected, people can lift 900 kilos. That's the statement. The null hypothesis is going to be generally accepted fact. Right? What is generally accepted fact, or opposite to whatever the statement is? people can lift 900 kilos in general. That's the statement. So I took people and then tried to ask them to lift the, lift the 900 kilos. If less number of people, right, less than 5% of the people are able to do this, this is significant. Because of this only people are able to lift it, right? If less than 5%, generally 0 people will actually be able to do 900 kilos, lift 900 kilos, right? So steroid is significant. Because of the steroid only the people are able to lift it, right? Right. So less than five people are able to do it. It is significant. This steroid is significant. In normal ground situation, less than 5 people are able to do it. It is significant. Because of this only they are able to do it. If it is, in general also more than 5 people are able to do it, then it is not significant. Your steroid may be giving some people, but it is not significant. Some giving capability to some people, but it is not significant. Maybe if they train a little bit more, they'll be able to do it without steroid also. That's what the concept is like.
No, Rama, here we understand the concept, but a small confusion. See, null hypothesis means it's commonly accepted. Means like it's already proven, right? So if it's already proven, again, why we need to like prove itself?
That is the point here. The significance test is for steroid. In null hypothesis situation, no steroid was injected. In general, it is. Right?
Yes, there is no steroids, but they can able to lift more than 5% peoples of 900 kgs. That is already proven, right?
Okay. When you say it is generally accepted, it means already
It's
people
already
are doing.
proven, right?
No.
Yes.
Okay. Yeah, so maybe you should take it as reverse, right? Reverse of whatever. If the experiment is about steroid, right? We say your steroid is not true. Generally accepted fact, or I should make the statement changed. Right? Your steroid is not valid. That's what I am saying. That is null hypothesis. In ground level situation, steroid was not injected, and we are saying that your whatever experiment's outcome is not significant. Is the null hypothesis. But to prove it, we should at least more than at least 5% of the times this should happen. Whatever the statement we made should happen to accept it. Accept the null hypothesis. Yeah, your point is right. Yeah, generally accepted fact, or your experiment is not significant. That kind of statement it is null hypothesis.
Okay.
Now p-value you understood, right? P-value, calculating p-value.
That too we got it.
We will not inject that drug and then try to do the experiment and see how many people, how much is the percentage of success. If it is more than 5, right, we accept the null hypothesis. If it is less than 5, less than or equal to 5, we reject the null hypothesis. In ground level situation, it is very rarely happening. That means the experiment is very significant. Whatever the drug is very significant. Got it?
Yes.
Is a statistical significance test. And tomorrow, right, we'll see one example on a drug one only. We'll see an example. And we'll see more about Z test and T test tomorrow. With this, right, I'll conclude the inferential first level of inferential statistics. We have second level where we'll actually cover ANOVA test, correlation test, and chi-square test, which are very useful. Maybe Monday we'll actually cover the what you call it as statistics and machine learning connectivity.